In 2014, a third-year mechatronics class from QUT was set a group project. These students were placed in groups to build a soccer robot for the small-sized league of RoboCup. These robots were to be capable of communicating between an Android phone and navigate a soccer field. The project required a great deal of collaboration between mechanical, electrical, and software systems. One group of students, nicknamed Heat Shrink, set out to design a solution. They called it the rerun.
Hi, I'm Jade, the lead mechanical designer in Group 8, or Team Heat Shrink. The mech system linked with the electrical and the software. As you can see here, it consisted of a differential drive, as this was familiar to other group members, and was cheaper than the alternative, being an Omni drive, which would require additional motors and an additional motor controller. This made it possible to come in under budget, whilst allowing for more money to be spent on other components. Using SolidWorks, a minimalistic and robust chassis was designed to be built out of 3mm MDF. This was then laser cut, assembled, and painted predominantly black to conform with the F180 rules for the competition. The mechanical subsystem needed to integrate with the electrical subsystem, including the PCB and power source, as well as the phone, which was going to be the vision center of the robot. As you can see, it consists of 3 levels. The bottom houses the motors and batteries. The middle level houses the PCB mirror, whilst the top houses the phone and the on switch. A cardboard shroud was used to encase the robot, as seen here, along with a plastic visor along the front, to stop the ball coming in past 20% as per the rules.
Hi, my name is Mark, and I was the Chief Electrical Designer for Team Heat Shrink. When designing the electrical system, I built it from the ground up. It needed to fit the requirements of the project, including size, functionality, and being cost effective. Starting with the power supply, the two 3.7 volt lithium-ion batteries in series provide electricity to the IO OTG and quadruple half-H driver simultaneously. This can be seen in the red and purple sections here. For ease of removal, female header pins were also used surrounding the IO board, seen in yellow here. Finally, the motor control, highlighted in purple, controls the 2 motors either side of the PCB. Although a kicker was not implemented due to the height restrictions on the board, PCB designs incorporated kicker circuitry. As you can see here, initial designs proved to be large, faulty, and costly. But with careful refinement, the PCB was reduced in size and made more cost efficient. Overall, the functionality of the final electrical system designed performed excellently whilst being small, robust, reliable, and cost efficient.
Hello, my name is Mitchell, and I am one of the lead programmers for Group 8's RoboCup F180 Small Science League robot. I was assigned the task of providing our robot with vision detection software based from the inputs of the inbuilt camera on the Samsung Galaxy S2 phone, and with adjusting the motors through the IO microcontroller PCB designed by Mark. Java was chosen as the primary programming language, as it is widely used in many other applications, and also works extremely cohesively while designing applications on Android. The vision code uses OpenCV contour filtering to outline objects and landmarks in the HSV color representation from the images gathered by the camera. It then analyzes the objects in the frame, removing any insignificant small contours detected in the image, as it is only interested in the larger, more prominent objects on screen. This allows the vision system to track the ball, goals, obstacles, and walls effectively, and therefore react accordingly. The data gathered was then sent to our other lead programmer, Gordon, who was in charge of the logic and navigation of the robot around the arena. Once he has worked out what the robot should do when it locates certain landmarks, these commands components were then sent to the IO, which drives the motors through the use of pulse width modulation, or PWM. This PWM movement control system allows for very precise regulation of the speed and direction at which the motors turn and increases the capabilities of the differential drive robot. All of this code was programmed into the Android application on the phone. The app allowed the user to visually see the contours the robot is identifying and using this to navigate itself around the arena.
Hi, my name is Gordon and I'll be looking after the logic and navigation for the robot. Now for movement for the robot, we've got three basic commands. It's either going to be an instruction to move to the left, to move to the right, or to go straight ahead. Now if I'm looking for the ball, to move to the ball, if I can see it somewhere on my screen, and this being an image of the viewfinder, if it is on the right side, the robot will turn its motors so that the ball is centered. If it's on the left, the opposite motors will operate so it becomes centered. When it's straight ahead, both motors will be running at the same speed, and what this does is brings the ball down on the screen. When it crosses my lower threshold, it tells me I've now got control of the ball, and we can move on to head towards the goals. Now the same logic applies when I'm trying to go around an obstacle. If the obstacle is on the right, instead of turning right, I will turn to the left, and that will make the object appear to slide out of the viewfinder screen. If I'm on the left, I'll turn to the right, and as I turn to the right, again, it disappears off the screen. If I'm coming straight at the object, the robot will follow the instruction not to go straight, but to stop and make a turn to the left. Once it's off the screen, it will then resume its normal pattern. When it comes to a wall, and the viewfinder is filled with white, the instruction is to turn around 180 degrees. And that is how the robot will be looking after navigation.